Hi, before starting, let me introduce Tristan. He's a third-year IT student at Macquarie University, and like many of the other students, Tristan had been wondering, how much will he earn once he graduates? So, he started researching salaries in the tech industry, but he was hit with headlines about income inequality and job dissatisfactions. Confused, he asked around, his friends, his family, even people already in the industry, and everyone gave him different answer. Why such different numbers? And more importantly, how much can Tristan expect to earn in his first IT job? To answer this, Tristan can use multiple linear regressions, or MLR, a statistical model that predicts outcomes based on several factors. In this video, I use MLR to predict tech salary and uncover which factors actually matter the most. First, I will talk a little bit about the origin and the definition of the model, so we can have an overview of what we are doing. So, who invented multiple linear regressions? The idea of regression dates back to the 1800s with Sir Francis Galton. He noticed that tall parents tend to have tall children, but not as tall as themselves, so he called this regression to the mean. That was simple linear regressions using just one factor. Later, Carl Pearson and Roland Fisher expanded on Galton's work to include multiple factors, and that's how multiple linear regression was born. So what is multiple linear regressions? This is a statistical model or method used to predict the values of a dependent variable based on two or more independent variables. Let's say you want to rate someone's salary. You might consider age, years of experience, job title, or education level. You can imagine that MLR is a recipe for a soup, and each predictors are the ingredients. The model gives us insight like, if you increase experience by 1 year, salary will go up by this much, assuming all other things stay the same. This approach is also used in finance, healthcare, or real estate to predict the house price, for example. So here's how the equation looks like. Y equal beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta n times xn plus epsilon. So the y is the thing that we are predicting. In this case, salary. Beta 0 is the base value or the intercepts. Beta 1 and beta 2 are the coefficients for each factors, and x1 and x2 are our predictors like experience, job title, education, and epsilon is the thing that we cannot explain. It's the error term. Now, let's talk about the dataset. We included age, years of experience, and salary. They are numerical variable. And for the categorical variable, we have job title, education level. But MLR can only use numerical variables. So how do we include things like job title or education? We will use something called dummy variable. So what is a dummy variable? This converts categories into numbers 0 or 1 to represent categories. We need dummy variable because MLR requires numeric input only. We will create n-1 dummy variable, where n is the number of values of the categorical variable. We exclude 1 to prevent multicollinearity, where two or more independent variables are highly correlated with each other. For example, job title has four options: analyst, manager, director, and engineer. We choose analyst as the baseline and create dummy variables for the other three. We can interpret the dummy variable for the manager as if the value is 1, the employee is a manager. If not, the employee will be an analyst. Same with education. High school was the baseline. Create dummy variable for bachelor, master, and PhD. So, our dataset will include job director, job manager, job engineer, edu bachelor, edu master, and edu PhD. Before running the MLR, we need to make sure 5 assumptions are met. I will check these assumptions by using Python. The first assumption is a no multicollinearity assumption. This one can be verified by checking the VIF score. In our case, all of the VIF score are less than 5, except for age, with a score of 5.24. Therefore, I will drop the age column and recheck the assumptions. After dropping the age column, all of the VIF score are now under the threshold of 5, which indicates the validations of these assumptions. Next, we will test the linearity assumptions using a residual plot. In the graph, the residual looks like they are scattered randomly. There's no clear pattern, trend, or curve, which means our model fits the data well. So the assumption is validated. The third assumption is the independent assumptions. We check this using the Durbin-Watson test, which helps us see if the residuals are related to each other. A value close to 2 means residuals are independent, and our result was 1.9, which is close to 2, so its assumption is met. We also check for the homoscedasticity. Homo means the same, and scedaticity means the scatter or spread. So for these assumptions, we want to check if the spread of the residual stays even no matter what the predicted value is. This is visible in the residual plot, which I created in the previous line, but I want to confirm this statistically, so I use the Gross-Bayes test. Our result is p equals 0.6, which is greater than 0.05, so the assumption is validated. Finally, for the normality assumptions, we check by plotting a histogram and a QQ plot. We can see that there's a bell shape in the histogram, and the QQ plot points forward along a 45-degree reference line, indicating that the residual closely follow a normal distribution. So the assumption is validated. So all of the assumptions are met. Let's perform the MLR in Excel. This is the dataset that we will use to predict the salary. Let's run multiple linear regressions to see how this variable predicts the salary. First, I will go to Data tab, click Data Analysis, and then select Regressions. For the Y range, which is the dependent variable we want to predict, I select the salary column. I press Ctrl Shift down arrow to quickly select the whole column. For the X range, which includes all our predictors, I select the remaining columns. Again, I press Ctrl Shift down arrow and press OK. And here's our regression results. Let's start from the top with the regression statistic. In the regression statistics table, I will focusing on interpreting R-square, adjusted R-square, and standard error. So, the value of R-square is 0.86, meaning about 86% of the variation in the salary is explained by our predictors. That is a very strong fit. Adjusted R-square is slightly lower, but still strong. It adjusts for the number of predictors, preventing overfitting. Why not rely only on R-square? Because R-square always increases with more predictors, even irrelevant ones. So adjusted R-square corrects for that. Last one is the standard error. The standard error is about 10,604, meaning that our predicted salaries are off by around 10,604 on average. Moving on to the ANOVA table. This table tells us if our model is statistically significant overall. The F statistics is 871, which is a large number. This means our model explains a lot more variation than a model with no predictors. And for the significant F, it's basically 0. That means our model is statistically significant. In other words, at least one predictor helps explain the salary. Finally, let's look at the coefficient tables. This is where we will interpret the individual predictors. First, we need to check the p-values. All the variables have the p-value less than 0.05, so they are all statistically significant. If any of the variable had a p-value greater than 0.05, we consider removing that variable and refit the whole model again. The coefficient of the intercept is 48,990, which is the expected salary when all other variables are zero. Looking at the years of experience variable, the coefficient is about 1071. That means each additional year's increase in the experience, the employee will earn $1,071 more. And for the dummy variables, these are compared to the baseline group, which in our case is an analyst with a high school diploma. For example, two employees who are analysts, the one with a PhD earns about $58,000 more than the employee with high school diploma. Another example is that a director earns about $25,000 more than an analyst with the same educational level. And that's pretty much our results. And let's move to the conclusion and key takeaways. In conclusion, our model explained 86% of the salary variation, showing a strong predictive power. All key assumptions are met, making the results statistically valid and reliable. Significant predictors include experience, education, and job title, with PhD holders and director earning the most. The model is practical and using interpretable coefficients to predict salary based on job title, education, and experience. Overall, this is a strong and valid model, indicating that education is the most significant predictor of salary. The higher educational qualifications, the higher salary. The job title also plays an important role in determining income. Additionally, each year of experience is associated with an average increase of $1,071 in salary. Based on the result of the model, here's the final salary prediction equations. Suppose Tristan has recently graduated, holds a bachelor degree, has 1 year of internship experience, and he is applying for an analyst position. The estimated salary that Tristan can expect to earn is $66,990. And that's the end of the video. Thank you for watching.